So before we get into working with stretches, vertical and horizontal stretches, I want to just review what we did in the previous video, which was horizontal and vertical reflections. So question 3 says, consider each graph, copy the graph of the function and sketch its reflection in the x-axis on the same set of axes. State the equation of the reflected function in its simplest form and state the domain and range of each function. So I picked 3b. We're working with this function right here, g at x equals x squared plus 1. And if you wanted to, you could kind of locate some key points on this curve. Okay, here they are. All right, we have the point on g at x. We have the points, so this is what our table would look like. When x is -2, y would be, you can see 2 to the left, you're up 5 units. And that could be found simply by looking at the graph that's given to you or filling a -2 in and squaring it. You'd get 4 plus 1, you'd get 5. -1, 2, 0, 1. We have 1, 2, and 2, 5. So those are those 5 points right here. I just picked them off the graph. Now the transformed function. All right. First thing I'm going to do is take this graph and reflect it in the x-axis. So here's the x-axis. This is the line of reflection. Remember, a reflection in the x-axis, that is a vertical reflection. The y values, okay, so these y values right here, 5, 2, 1, 2, 5, they would switch signs. So they're all positive, they're going to all become negative. Okay, so I'll call this h at x. I'll come up with the equation of it in step 2, but I'll just finish this part first, and then I'll draw that. So my x values, my y values, my x values aren't going to change. -2, -1, 0, 1, and 2. They're going to stay the same. Pardon me. -2, -1, 0, 1, and 2. It's the y values that are going to change sign. So remember, with a vertical reflection, you multiply all the y values by -1. And that would do this. It would make all the positives negative. So I would plot these points, 2 to the left down, 1, 2, 3, 4, 5. 1 to the left down, 2. Don't go left or right, so 0, -1. Right 1 down 2, right 2 down 5, and then I would join those with a nice smooth curve. And there is step 1 done. Okay, so we'll call this 1, this 2, and this 3. All right, so there's step 1. I've reflected the g at x equation in the x-axis. State the equation of the reflected function in simplified form. Okay, so remember, when you reflect something in the x-axis, all right, it means the whole output of the function is multiplied by -1. So that means the transformed equation h at x, it requires me to multiply the right-hand side by -1. So that negative is going to get distributed over both terms. So in this case, h at x is going to equal -x squared minus 1. So the equation here, -1, sorry, -x squared minus 1. So if you filled a -2 in for x and you squared it, that would give you a 4, and then multiplied it by -1, that would give you a -4, and then subtracted 1, that would give you a -5. So now this formula coincides with this. There is the equation of h at x. So there's step 2 done. And state the domain and range of each function. Well, I think we can agree that the domain of the blue and the red would be x such that x belongs to the real numbers, okay, because it goes left forever, right forever. I didn't have to go from -2 to +2. I could have went from -2 to positive infinity. And same thing for the red. Okay, so step 3. For domain of f of x equals x squared plus 1, the domain is going to look like this in set notation. X such that x belongs to the real numbers. And the range will be y such that, let's look at the blue curve. What's the lowest y value on the blue curve? Okay, it's right here. What's the height of that? The height of that is 1. So we're going to say y such that y is greater than or equal to 1 because all of the points on the blue curve are above a height of 1. And we'll say y belongs to the real numbers. Now, in interval notation, it will look like this. Okay, from negative infinity to positive infinity. That is an interval for the domain. For the range, it would be from 1 to infinity. So it's always your smaller number first, and then your larger number second. Okay, 1 to infinity. Notice I put a square bracket in front of the 1 because it can equal positive 1. If it was just greater than 1, this would be a round. And realize you'll never obtain a negative infinity or a positive infinity, so they'll always have a round bracket preceding it or a round bracket after it. And for, that wasn't f at x, sorry. This was g at x. And I called my transformed curve h at x. So for h at x equals negative x squared minus 1, the domain is still x belongs to the real numbers. Or from negative infinity to positive infinity in interval notation. The range will be y such that y is, and careful with this one. This one's got a maximum height at this point, a maximum y value of negative 1. Everything else is below negative 1. So we'll say y is less than or equal to negative 1. Y belongs to the real numbers. Or from negative infinity to negative 1. Now notice, some people might want to put the negative 1 first, but negative infinity is definitely less than negative 1. So it's always smaller number, comma, your larger number when you're doing interval notation. Round bracket precedes the negative infinity. Could be a round bracket after the negative 1, but it's a square bracket because it can equal. It would be round if this just said less than negative 1. All right, so that's kind of reflections, a little recap. Now we're going to talk about stretches. Now a stretch, unlike a translation or a reflection, changes the shape of the graph. All right, if it's the output of the function, all right, we're talking about this is vertical stretch. A couple things. Vertical stretch and reflection are in or about the x-axis. But remember, a vertical stretch for the mapping rule, anything vertical is going to affect the y values. So we'll go A times y. So it's essentially the same thing you did yesterday with reflections, only yesterday your A value was a negative 1, or in the previous video. Today it could be anything. Okay? It could be 2, 5, it might even be a negative 5. All that means, if it's a negative 5, is that you are actually applying two transformations, a reflection and a stretch. You would be vertically reflected in the x-axis because it's a negative, and you would be vertically stretched about the x-axis. So a couple things, if we read this, is a vertical stretch of the graph about the x-axis by a factor of absolute A. So when you're stating the stretch factor, if someone asks you what the stretch factor is, always state it as an absolute value. If A is a negative, then you also have to say the graph is reflected in the x-axis. If the A value is a positive, so greater than 0, you wouldn't have to say there would be no reflection in the x-axis. So if it's the output, vertical reflection in the x-axis, vertical stretch about the x-axis. If it's the input, horizontal reflection in the y-axis or horizontal stretch about the y-axis. So this is horizontal stretch. And with horizontal stretch, okay, yes, it is in the y-axis or about the y-axis, but it's the x values that are going to change. And remember the parameter we used yesterday was b. And actually with this one you have to use the reciprocal, so it's 1 over b times x comma y. So there's a little catch with this one. All right. Again, you would state it as an absolute value if you're stating the stretch factor. But if you're talking about reflection, well, the only way there's reflection is if the b value is a negative. So if the b value is also a negative, you would have to say it's reflected in the y-axis. This just says that scale factors between 0 and 1 result in a point moving closer to the line of reflection, and a lot of times we refer to these as not vertical stretch, but vertical compression. I find this textbook starts out really good using the word compression appropriately, and then as we move through it later on, they just kind of call everything a stretch factor. So I'm not going to get too bent out of shape if you call it stretch all the time, but I'll explain what it means by a compression. That just means your scale factor would be something like between 0 and 1, so it could be a half, 2/5, 0.75, whatever. Okay? So here's an example. Notice where the 2 is here. It's in front of the f of x. Okay? That means multiply the whole right-hand side by 2. It's the output. So in this particular case, that is an a value of 2. And if a equals 2, we can say there is a vertical stretch about the x-axis by a factor of of 2. Okay, period. There is no vertical reflection in the x-axis because this is a positive. Now, if there was a negative here, okay, my a value is a -2, this line wouldn't change. Vertical stretch about the x-axis by a factor of, remember it's absolute a, so absolute -2 would be 2. But I'd also have to say and reflected in the x-axis, or and vertically reflected in the x-axis. I only have to say that line about being reflected in the x-axis if there is a negative attached in front of that 2. Mapping rule is going to look like this. X comma y will become x comma 2 times y. So that means I'm just going to take all of these x values, do nothing to them, and I'm going to take all of these y values, and I'm going to multiply them by 2. So my transformation, or my transformed points, would be -6, comma 8, -2, comma 0, 0, comma 4, 2, comma 0, and 6, comma 8. So check it out. The x values did not change. They're the same. The y values, I doubled them. Why? Because I'm vertically stretching this function about the x-axis. So what it's telling me to look, saying 2 times f of x. So here's f of x. That's where I got these blue points from, just from this picture. And I'm going to double all the y values. And here's what my transformed curve should look like. Okay. -6, comma 8, -2, comma 0, 0, comma 4, 2, comma 0, and 6, comma 8. Now notice, there's a couple of points that did not change. That is because they are on the line of reflection, they are called invariant points. So in this case, the invariant points would be negative 2 comma 0 and 2 comma 0. For f of x, the domain is, now be careful, f of x, that's this guy. Domain, we're talking about the x values, so there's no arrow on this end and there's no arrow on this end. So using set notation, you would go between negative 6 and positive 6. So we would write x is greater than or equal to negative 6, but less than or equal to positive 6. X belongs to the real numbers. I think that's what most of you are used to, set notation. Okay? But remember, in interval notation, it's your smaller number, comma, your bigger number. And in this case, since it can equal negative 6 and it can equal positive 6, you would use square brackets. So it would look like this, negative 6 comma 6 in square brackets. The range, okay, let's get rid of these. Let's box it in on the top and bottom if we can. No arrow, so it should be pretty easy to do. Okay, it's got a maximum height of 4. It's got a minimum height of 0. So again, we would say y, such that y is greater than or equal to 0, but less than or equal to 4. And I think that's what most of you are comfortable with, from 0 to 4. All right, and in interval notation, that would be 0, comma 4, both in square brackets. All good. Now, think about for the domain of g at x, the transformed curve. So g at x is this red one, the transformed one. The domain is still from negative 6 to positive 6. Well, that makes sense because we were talking about a vertical stretch. I did not change the x values. So the domain for g at x is the same as the domain for f of x, from negative 6 to positive 6. The range is going to change. How do I know the range is going to change? Because I doubled the y values. So how should the range change? It should go from, it was 0 to 4. If I double it, it's going to go from 0 to 8. Okay, I doubled the y values. I doubled the range. So the range will read y such that y is greater than or equal to 0. So that's how you read that. Y is greater than or equal to 0, but y is less than or equal to 8. Y belongs to the real numbers. Okay? Or from 0 to 8. So that is an example of vertical stretch. Part B, I won't go through the whole thing, but this would be, notice the A value is still an A value. So A is 1/2. Okay, but I would say this is vertically, instead of saying stretched, it's probably more appropriate to say vertically compressed about the x-axis. So vertical reflection and vertical stretch are in the x-axis, and it's by a factor of 1/2. There is no vertical reflection in the x-axis because this is a positive 1/2. Well, there's no negative there. So all I would do here is nothing to the x values, multiply the y values by 1/2, or divide them by 2, same thing. And you can see, all right, the original, the blue curve, became shorter. And again, you would be manipulating the range here. Okay, let's look at one example of horizontal, and then you can move on to your own. Okay, so note the difference between horizontal and vertical. Again, the parameter, some people might look at this and say, well, is that an A value or a B value? Well, no, if it's an A value, it would be the output. This 2 would have to be in front of the F. If it's a B value, it's going to be inside the brackets because it's the input, the X values, that are getting multiplied by 2. All right? Now, in this particular case, here's the catch. B looks like a 2, all right? It's exactly as you see it here. But this represents a horizontal compression by a factor of 1/2. Okay? With the b value, you always have to take the reciprocal. So if b equals 3, HSF equals 1/3. If b equals 2/5, HSF, the horizontal stretch factor, would equal 5/2, or 2.5. Okay, and that comes from carefully reading this. Look, in the equation y equals f of x plus b, it's a horizontal stretch of the graph about the y-axis by a factor of 1/b. That means take the reciprocal. Okay, so note that carefully. Horizontal compression by a graph of, by a factor of 1/2. I forgot to say it's in the y-axis too. I should have added horizontal compression in the y-axis before I said by a factor of 1/2, but it's all good. Okay, so think reciprocals. Don't have to do that when we're talking about vertical stretch, only with horizontal. Okay, the mapping rule is going to look like this: x comma y. What am I going to multiply the x values by? Here's the debate. Do I use 2 or 1/2? Well, the answer is 1/2. You multiply it by the horizontal stretch factor. So if b is 2, the horizontal stretch factor is 1/2. If b is 1/2, the horizontal stretch factor would be 2. All right, so my points are going to become -4, 4, that would become -2, 4. -2, 0, that would become -1, 0. 0, 2 remains unchanged. 2, 0 would become 1, 0, and 4, 4 would become 2, 4. All right, let's see. All of the x values were cut in half. I multiplied them by 1/2. The y values, 4, 0, 2, 0, 4, they did not change. Now notice these points were a little different from the previous graph, but -4, 4, -2, 0, 0, 2, 2, 0, 4, 4, that's where these blue points came from. And if I delete the black box here, you can see that the point -4, 4 became -2, 4. The point -2, 0 became -1, 0. There's 0, 2, didn't change. 2, 0 became 1, 0. 4, 4 became 2, 4. What is the invariant point? All right, that's this point here, 0, 2. The domain of f of x, check it out, goes from no arrows on this side, no arrow on this side. That curve exists between x values of -4 and +4. I would write that as x is greater than or equal to -4 but less than or equal to +4, or from -4 to +4. The range of the blue goes from 0 to 4. Okay, there it is in interval notation. Now, for g at x, the transformed curve. Okay, see if we can do it without even looking at the picture itself. What did I do when I manipulated these points? Did I manipulate the x's or the y's? Well, check it out. The x's, I cut them in half. So if you're manipulating the x's, you're definitely changing the domain. So the domain went from -4 to +4. If I cut the x values in half, I cut the domain in half, so it should go from -2 to +2. In interval notation, -2, 2 in square brackets. And the range didn't change it. Okay, it was from 0 to 4. It's still from 0 to 4. I did not manipulate the y values. Okay, so there you have it. And perhaps you can try this one on your own or check the notes in the Teams app. I have this one complete as well. I will just go through one thing. Here's an example where your b value is 1/2. That's what you get from the equation. That means your horizontal stretch factor about the horizontal stretch factor of 2, okay, the reciprocal of 1/2, about the y-axis. So remember, horizontal stretch, horizontal reflection are in or about the y-axis. Vertical stretch or vertical reflection are in or about the x-axis. Okay, so you can check the answer to this within your notes, and then you can try these questions for homework.